Hello, everybody, and welcome to the third session of the training for policymakers about quantum technology. Today, we have a session, as expected by you, about sensing and metrology. And there has been a few changes in this about this session, which I will announce you at the moment. Let me open a few slides that I wanted to share with you. The surprises never stop. This has been so far the most surprising presentation session, at least during the organization of it. And the surprises continue. That should be working by now. And I will do the slideshow. Here we go. And before the start, in any case, before announcing the agenda, I'd like to present you the organizers of this session, which is Costanza Toninelli, who is a professor in experimental physics at CNR-INO. And so it's me, Oxana Mishina, and I'm the senior fellow at CNR-INO. And our PhD student, Diana Tartaglia, who is doing her PhD in quantum technology in the sector of communication and impact on society. As I told you, the agenda of today is going to be slightly different. While preparing the talks about sensing and metrology, we have realized that the two topics has grown up so much that it would be too few time for them to be put together. And we decided that today we will present only about sensing, and we will set up a next session that will be dedicated to metrology. And this is the first change of the program. And the next change of the program is that, unfortunately, the speaker, our first speaker, and also the moderator of this session, Thomas Schmidt, who is the member and of QuIC, the Quantum Technology Industry Community of Europe, and also a director at Bosch company. He unfortunately got sick and cannot be with us today. This is the second change. And the third, and I hope final, but we don't know until the end of the session, is that Morgan Mitchell, who is our second speaker today, will take a place and present the slides that Thomas has prepared for us. So this is quite a lot of changes, and we will try to cope with it as best as possible. And the program will be like this. So after my presentation of Morgan, I will give the word to him, and Morgan will make an overview about the sector of sensing, and maybe with a little glance on metrology. Afterwards, this will last between 7 and 10 minutes. Afterwards, we will address a few questions, and I ask you kindly to put your questions in the question and answer section of this webinar, so that we could pick up the questions to answer after the first talk of Morgan. And then when we will get to the points that are more addressed in the presentation that Morgan prepared about sensing use cases, Morgan will start his second presentation, which will also last between 7 and 10 minutes. And then we will continue with questions and answers, and we will have a nice and sweet half an hour for discussions. And in the end, Morgan will conclude the session with the take-home messages. So that's the plan. And we will do our best to stick to it, but keep an eye that this is a lot improvised session, as we had a lot of changes this morning. Okay, just to remind you that we projected this training with a scope to help the attendees to gain knowledge to take informed decisions, and also to help cooperate with peers from other countries on this topic. And last but not least, it would be great if we will help you to sustain a conversation on the quantum technology topics with experts in the community. So we try to update the data about you, because I think you are quite curious on the attendees of the session. So we had 78 registered participants. And on the left side, you see the distribution over the countries. So we see that this time Spain participants peak, and German participants are always at a very high level. But we also have a lot of participants from Italy and Luxembourg. Oh, Luxembourg, I'm particularly happy because this clearly most likely the policymakers and the European Commission that are so kindly asked us to introduce this training into the QuIC program. And on the right side, we also see about your background in quantum technology. So the questions was how much you've heard about it, and most of you are very well updated and informed. But there are still a few people who are curious to learn and never heard about it. So I'm sure Morgan will be satisfying all the needs of our attendees today. And with this, I'd like to thank a lot all the members of QuIC who helped us to prepare this training and advised us about speakers and also about the policy for implementing the training. And I think that's time to introduce our next speaker, Morgan Mitchell, who is a professor at ICFO, which is the Institute of Photonics in Spain. And he works there since quite a while. And I had my pleasure to work with him as well some time ago. And I'm very happy that we are going to be together in this very surprise session. So I welcome you, Morgan, to the stage. Stop sharing.
Thank you, Oksana, for that nice introduction.
And could I ask you, Morgan, to turn on your video if that's not a problem?
It is not allowing me to start my video.
Oh,
my personal video.
Let me check to try to solve this problem. Would it allow now?
Yes, it looks like it. Okay. Okay, thank you, Oksana, for the introduction. Thank you also to Thomas Strohm, who prepared most of the slides that I'm going to show in this first part. A few of the slides will be my own, and those will be labeled with ICFO, whereas the others will be labeled with Bosch. So I'm going to start really at the beginning, at the basics, talking about quantum sensing. What is a sensor? A sensor is a device that is sensitive to some physical quantity, for example, temperature, electric or magnetic field, acceleration, rotation, length changes, or in fact, a great number of physical parameters that could be detected from the environment. And a great example that everyone is familiar with is a mercury thermometer. The property of mercury that changes with temperature is its volume, and we can see that directly, and that then gives us a measurement of the temperature. What is a quantum object? It is an object which behaves according to quantum mechanics. So that could be an atom or a photon, the spin of an electron. There are, again, many particles, many systems, superconductors also, that behave according to quantum physics. And that gives them access to a different set of operating principles, which include quantized energy levels, quantum superposition, and entanglement that are not available to classical objects. So then what is a quantum sensor? A quantum sensor is a quantum object that is used as a sensor. It can also be an ensemble of many quantum objects that are used as a sensor. And why are we using quantum sensors? Well, typically they have very high precision, often far beyond what you can get with a classical sensor. They're based on fundamental particles like atoms or electrons. And so they don't need to be calibrated because anyone who uses those atoms will have the same atoms. And they typically can be miniaturized and made very robust, which gives them further advantages. And an example of how precise they can be comes from metrology, comes from the field of atomic clocks. And the best atomic clocks now have a precision that is better than 1 second in the time since the Big Bang. So this is something which is just unthinkable with any kind of classical technology, but it's now done with quantum technologies in metrology. Here's a good example which comes from Bosch about the advantage that you can get in quantum sensing. So these are magnetometer technologies. These are all solid state technologies which can be miniaturized to the point that you can put them into something like a mobile phone. And they're based on different physical effects which happen in semiconductors or other materials. And so these are all what we would call classical sensors. And the sensitivity here is given in terms of the smallest magnetic field that could be detected. And if you look at the progress in that field, then you get this extrapolation of the state of the art, and you expect them to get better with time. And then when you go to a quantum sensor, which in this case is a nitrogen vacancy center in diamond, then you start to see both a better sensitivity, a much better sensitivity, and you start to see a rate of improvement which is still better. And so these are examples of devices that were made using this technology by Bosch, and they have recently gotten down to sensitivities which are comparable to the fields that are produced in biomagnetism. And so they start to be interesting for medical applications. And this is a good example of something you can do with quantum technology that you could not do, or you could not do in the foreseeable future with classical technologies. A comparison between different quantum technologies. Quantum cryptography and quantum computing are very well-known quantum technologies. Quantum cryptography is maybe the first one to hit market, that there have been for about a decade systems that you can buy to do quantum cryptography between different points, and that area is advancing rapidly. That communication infrastructure is being built especially in China, the US, and the EU. Quantum computing is still on the horizon. That is also a very rapidly progressing field, but we don't expect that practical quantum computers will be available and better than classical computers still for about a decade. Quantum sensing is heterogeneous, that there are many quantum sensing technologies, some of them like atomic clocks, gravitation detectors, single photon detectors were introduced already before quantum cryptography. And many of the devices that we're excited about now in quantum sensing are still over the horizon. And so there's a mix here of improvement of existing technologies and revolutionary new technologies that will open new possibilities. If you look in terms of money, you can see the established technologies. So there is already a sizable market for quantum sensing technologies, and that is expected to grow in the coming years. It should be said that these projections of market size are always, because they're forecasts, they're always somewhat speculative, but there's also a large scatter here in the predictions. And so that's characteristic of any quantum technology, that we know that they have great potential, and there's a question of how well we will be able to implement them. I would like to underline here that these are not competing technologies, and I illustrate this with a very well-known example here. This is a recent mobile phone, and we know that a mobile phone is both a communications device and it's also a portable computer, and it's very impressive for those features. At the same time, modern phones have a large number of sensors in them. Obviously, there are image sensors to take pictures, but there are many other sensors here: accelerometers, gyroscopes, LiDAR, GPS. And it's the synergy between the sensor capabilities and the computing capabilities and the communication capabilities that really make the mobile phone the incredibly useful device that it is. And you can see this right here in the branding on this Nokia phone. They label this as a 50 megapixel AI camera. So right there, you see the sensing and the computing aspects side by side, integrated together in such a way that one is supporting and enhancing the capability of another. And then, of course, once you've taken your 50 megapixel AI enhanced photo, then you send that using the communication capability. If we look at where quantum sensing can have an impact, there are simply too many potential use cases. So here are different sensor types: initial sensing, which is rotation, acceleration, and gravity; magnetic sensing, electromagnetic, and optical, in different major sectors of the economy. So health, transportation, energy, etc. And what you see is that this is a small number of the applications where quantum sensing can either enable something or improve it, or make it more accessible or less expensive. And so it's not possible to describe all of these. There are so many applications for quantum sensing. Okay, so we will talk today about a few of the most promising that are either recently developed or on the horizon. This is quantum measurements of gravity, and this is based on atomic interferometry, and it has applications in civil engineering, mining, earth monitoring, defense. Atomic clocks I will not say very much about, because there will be a separate session on metrology, and atomic clocks are metrology. Quantum magnetometers I will talk about quite a bit. These are very interesting for many applications, ranging from health, brain imaging, heart imaging, to earth monitoring for environmental applications. Gyroscopes sense rotation. So this is also based on atomic interference, sometimes optical interference, and that is very interesting for positioning, orientation, and it's often used in support of other technologies. Quantum imaging takes advantage of the incredible ability we have to shape non-classical light, which is to say to manipulate photons in quantum states, and it allows us to get improved resolution and other important features, and it's used in, for example, radar. It allows you to do better spectroscopy, biological imaging. Gas sensors. It turns out that atoms are a fantastic way to detect the presence of gases in a molecule-specific way. And so that can be used, for example, in trace gas detection, which has environmental applications, but also health applications. So these are a few of the applications that use cases that we can talk about today. So with that, I end the first presentation, and I understand that there will be a question and answer period now.
Exactly. Thank you very much, Morgan. This was an awesome introduction with tons of materials. I have to say that at the moment, in the question and answer part, there are no questions, but our attendees, they were kindly asked to write down their questions when they registered. And so I will now read a couple of questions from that list. Everybody is welcome to we have a question to Giovanna, but this part will go to the next session. And then we have a question to how far is quantum sensing to be used in the field of astronomy?
Okay, this is this is a very interesting question. It's also a very active topic. It turns out that there is something called the Rayleigh curse, which is related to the Rayleigh resolution limit, which tells you how close two objects can be and still be observed as two distinct objects. And this is very important for astronomy. If you have a telescope of a certain size, it will be able to resolve two objects, which could be, for example, a star and a planet orbiting the star. And if there's a limit on the resolution, which is related to the size of the telescope, then you either have to build a bigger telescope or you have to do something clever. And recently, it's been suggested, theoretically, that it should be possible to do something clever. It should be possible to use interference of the photons coming from the system that you're imaging, so from your astrophysical object, and to interfere them in a particular way, which improves the resolution. And there have been proof of principle experiments on this, but so far there hasn't been nothing which is done in a real telescope for astronomical or astrophysical observations. So I would say that that is still, it's always difficult to predict how long it will take things to develop, but I would say that is still 5 or 10 years ahead for actual application in real telescopes.
All right. That was extremely interesting to know. And I hope we have satisfied also the person who asked the question. And this is 𝗔𝗴𝗱𝗱 from Riga. And now there is one more question to this session, which is, let's say, more suitable to one of the upcoming sessions, but let's try to twist it. So the question is the following: when can one expect a functional quantum computer in EU made in the EU? So I think we could address this question maybe in regard to sensing from the point of view that Morgan already mentioned, that technologies that do not compete, they actually cooperate. And this is something also that interested me a lot, how quantum sensing is actually useful for quantum computing, because you gotta detect those quantum states when you do quantum computing. No, so I always had a thought that quantum sensing is already actually in use in quantum computing. So could you go a little bit more in details about this connection between sensing and computing?
Okay. Well, first of all, I'm not an expert on quantum computing. There are already European companies that will sell you a quantum computer and or a quantum simulator, which is a special purpose quantum computer. And then as regards the use of quantum sensing in quantum computing, yes, I think your point is very insightful, that if you are going to, what we say, read out your quantum computer, if you're going to learn what the result of the calculation was, then you're going to be measuring quantum systems. And that then becomes a sensing and metrology task that you need to precisely measure what your quantum systems have done. So for example, if you were using single ions or superconductors as your qubits, then to know what state they have taken on, then you need to do some sensing. And so there will, of course, be a role for quantum sensing in the implementation of quantum computing.
Thanks a lot. So you have unwound my, let's say, doubts and confirmed my expectations. So I'm really happy. And I think as we have satisfied all the questions from the question and answer list of the registered people, and let me check again if we have got new questions and answers. No. Lydia, may I ask you for a quick check, just to write a test question and answer, just to be sure that they are active? Because I start to wonder that maybe something is wrong. And while we are doing this check, I would do a quick, now we have to pass formally from the presentation and of the overview. So we would thank very much Morgan for presenting the presentation of Thomas Strohm. And we, of course, thank a lot Thomas Strohm, who made this presentation and shared it kindly with us and cooperated in an instant manner this morning, nonetheless, not feeling very well. And now I'll introduce you our next speaker, that not very surprisingly will be again Morgan Mitchell, but I wanted to talk a little bit more about him because now I should play the role of moderator. So if you allow me to share my screen again, I would tell you what a GPT chat gives me as a quick response when I asked him or her, I don't know, this device, to extract 5 key points about Morgan Mitchell from his infinitely long biography, because I wouldn't be able to read it all now. And of course, we already know that he's a professor and at ICFO, and it's an ICREA professor. At ICFO, they have very special statuses, as they are not a usual public institute. And he's specializing in atomic optics research, as you probably have already guessed from his first presentation. So his research focuses on utilizing quantum effects and to enhance the sensitivity of atomic instruments like magnetometers. And this you will notice even more in his following presentation. He has made significant contribution to quantum sensing, including path entangled states, squeezed light, and entangled photons for precise optical measurements. Professor Morgan Mitchell's work extended to the development of minimized atomic gyroscopes and optically pumped magnetometers for applications in medical imaging. He has also collaborated on entanglement-enhanced atomic clocks and innovative applications in atomic sensors, such as magnetic resonance, spectroscopy, and imaging. I think GPT Chat did quite a good job, and there are many more points about Morgan that you have already seen in his biography, and I welcome him back on stage to tell us about sensor use cases.
Okay, thank you, Oksana, for that very nice introduction. It's definitely a first for me to be described publicly by ChatGPT. Let me share my screen here. Are you seeing this?
Yes, quantum
Great.
sensing use cases.
Okay, great. So thank you for the introduction. So now I'm going to talk more specifically about use cases and go into a bit more detail and talk about what is exciting about them and what we think they can do in the near future. So as I said in the previous presentation, there are too many use cases and we have to make some kind of selection. And the selection that I make is going to be oriented around activity in the quantum technologies flagship, which provides excellent examples of use cases and of projects pursuing those use cases. One thing I'm not going to talk about is atomic clocks because there will be a separate section on magnetometry, and so I'm not including here on metrology, and so I'm not including the metrology projects in this presentation. So in the first generation of flagship projects, there were these sensing projects. So Maximal used atomic sensors, developed a variety of atomic sensors, all based on the concept of miniaturization. And you can see a product of this here. This is a miniaturized atomic clock, which has been reduced in size. This is an entire physics experiment with lasers and atoms and detectors, all reduced to a size that is a chip that can be soldered into a circuit board. Asterix and Metabolics are projects that use nitrogen vacancy centers in diamond, and those allow extreme sensing, especially magnetic sensing, but also other parameters at the nanoscale and at the microscale. So let me first talk a bit about one of the targets within Maximal. So this is magnetic brain imaging, also known as magnetoencephalography or MEG. And the way that works is that any brain activity involves currents traveling in neurons, and those currents generate magnetic fields, and those magnetic fields extend outside the head, so they can be detected in a non-invasive way by putting sensors close to the head. And this is done by placing many sensors close to the head so that a map of the field distribution coming out from the head is collected. And then a computer can be used to calculate where inside the brain the current was that produced that field distribution. And this is a unique capability in biomedicine, in brain science, because it's the only thing that we have that gives us both spatial and temporal resolution to see everything that is happening inside the brain. It's also a very demanding problem. It requires sensors which have an extreme sensitivity. The signals, strong signals, are of order 100 femtotesla, and so the sensors need to have about 10 femtotesla sensitivity. They also need to be small so that you can place many of them around the head, and they need to be fast so that you can observe the fastest brain events. And because this is a unique capability, it's very useful for understanding how the brain works. It also has medical applications. For example, in epilepsy, it's used to characterize the start locus of the epileptic events, and that's something which is done in preparation in extreme cases for surgery. And that's an important problem. There are about 300,000 new cases of epilepsy in Europe that would be candidates for surgical intervention. Mild traumatic brain injury is also a very common brain disorder, brain disease. And that's something which is difficult to diagnose otherwise, and magnetoencephalography has a role there. The same magnetic sensor technologies are also used for measuring the heart, which is magnetocardiography, and measuring muscles, which is magnetomyography. This is an example of a commercially available quantum sensor. So this is a superconducting magnetoencephalography system. This is me with my head inside the helmet of sensors. And this is capable, something you can buy now, but it is large and expensive, and it is based on superconductors, and thus it requires a supply of liquid helium. There is a strong effort in the field to develop atomic sensors with the same capabilities, and that is illustrated here. Each one of these is an atomic sensor, and that can be operated without the liquid nitrogen, and so it's much easier. And also because it can be used in a wearable fashion, it can be personalized to any given patient, and it is simply much more convenient. And so within the Maximal project, we developed sensors that have these capabilities, high sensitivity, small footprint, and good time resolution, all based on miniaturized atomic vapor cells, which are the heart of this instrument. And that work continues in an EIC transition project, which is called OPM-MEG, for optically pumped magnetometers for magnetoencephalography. Maximal produced these magnetometers, but it also contributed to atomic clocks, as you see here, gyroscopes, microwave sensors, terahertz sensors, gas sensors. So there are many different sensing tasks that can be approached with these same miniaturized atomic sensor technologies, and with many applications ranging from space to health, to high-speed electronic technologies, inertial navigation. There are many different applications for these. Okay. Meanwhile, 𝑆TRx and Metabolics, working with diamond nanosensors, were able to do similar magnetic sensing. In 𝗏, this is in two-dimensional materials, which are something that is very exciting as a future technology. Metabolics studied the use of nitrogen vacancy centers for doing magnetic resonance imaging on individual proteins, for example, this myoglobin. And that's just the beginning of what they were able to do. The nitrogen vacancy center is a multi-purpose sensor. It can be used for temperature sensing, for strain sensing, magnetic field sensing, and other applications are pursued in these other projects also. Then in the second generation of quantum flagship projects, then we start to see new technologies, gravity sensors, mid-infrared sensors, optical coherence tomography, which is naturally an optical technology, as well as two more diamond projects. So let me tell you a little bit about what is going on in those technologies. So a quantum gravity sensor uses atoms to detect the gravity. So the atoms are caused to interfere, and the phase of the interference is introduced by gravity. And because they are so small and their wavelength is extraordinarily small, then these atoms become extremely sensitive to gravity. And because they're atoms, then they give you a self-calibrated measurement of the gravitation that you're measuring. And this is something which can be miniaturized to give you a portable sensor. This is an example from the company IXBlue, where they took one of these sensors to Mount Etna, and they observed the flow of magma under the ground in the evolution of the volcanism in this situation, and that is where this project FICOS is aiming, is to have portable sensors which can be used for a number of earth science tasks, which will have important impacts. For example, reduced environmental impact due to mining, improved utilization of geothermal energy resources, and eventually to aid in CO2 sequestration to mediate climate change. So many applications in the geotechnical field for these gravity measurements. Optical coherence tomography is a technology which exists and is used for measuring the eye. So this is a very important technology for looking at things like retinal degeneration and other diseases. And it is currently done with classical light sources, but quantum light sources offer an important advantage that they allow you to have simultaneously a high resolution and to avoid distorting artifacts that come about through dispersion of light in the material. And so this is the project Sequoia. Then the project Miracles is working in the mid-infrared to develop, again, optical techniques, so quantum optical techniques, including quantum light sources for the mid-infrared, integrated photonics to manipulate light in the mid-infrared, and quantum light detectors for the mid-infrared. And these are technologies which already exist in other wavelength ranges, but there's a lot of motivation to apply this to the near-infrared, because the near infrared is where you get a fantastic wealth of information about chemistry with many applications. So here you see for this wavelength range, this mid-infrared wavelength range, you see all of the absorptive spectral lines that you can have in different molecules that you can find in the atmosphere, or for example, in a breath sample. And that is the utility of this for chemical identification, with applications in environmental monitoring, industrial process control, medical diagnosis. Okay, and then going a bit beyond what is currently able to be supported by the Flagship, but which has, again, great potential. So gravity sensors, again, there is a lot of interest in putting quantum gravity sensors in space. I illustrate why that is with this. This is a joint US-German mission called the GRACE mission and GRACE follow-on, where 2 satellites orbit the Earth and experience the Earth's gravity, and with great precision, they measure the gravity of the Earth, but at a global scale. And here's one of these 2 satellites when it's under construction and testing before being launched. And this pair of satellites can produce a fantastic map of the gravity of the Earth, and it is so sensitive that it can see the change of, for example, water levels in the ground corresponding to centimeters of height. And so you can see here changes in the gravity of the Earth over recent years. And you can see some alarming things, for example, a loss of mass in Greenland, which corresponds to the melting of the Greenland ice sheet. Also in Antarctica, you can see accumulation of water in the Amazon. And this kind of sensing can be improved quite a lot through the use of atomic interferometers, atomic gravity sensors. So that is something which is on the horizon, but is actively being studied. And then another one that's on the horizon is this. When you get a magnetic resonance imaging, you probably know that that is a large and expensive device. And a large part of its size and cost comes from the requirement to have a very strong magnet. So these use superconducting magnets, which need to be cooled to cryogenic temperatures. And that is because it requires a very strong magnet in order to polarize the nuclei in the patient's body in order to generate a signal that can be picked up by a classical sensor, which is a radio frequency coil. And so you might ask, well, if you replaced the classical sensor with a quantum sensor, could you reduce the requirement for the magnet and thus make the system cheaper? And you could, for example, use a quantum sensor like this atomic magnetometer, and sorry, this superconducting magnetometer. And that's in fact been done. So here are images that were acquired not at Teslas, but at microteslas of strength using exactly this kind of machine. And then you can ask, well, if that works, then why not replace those quantum sensors with these quantum sensors? And then you may have a magnetic resonance imaging solution, which is completely free of liquid helium and would be very convenient to be used, would be portable. This would be a major advance. Okay, so we're not there yet, but this is something which is on the horizon for quantum sensing in ultra-low field magnetic resonance imaging. Okay, so that is the end of my slides. Thank you for your attention, and I'm happy to take questions.
Thank you very much, Morgan, for this extremely insightful presentation. Looks like the cost for imaging is going to drastically go down, and hopefully this will also reduce the lines that people have to wait for doing such images, and also accessibility for them worldwide, which is a super nice progress for the future inclusivity in our society. So I'm quite excited about it. And we have just got a first question. And actually, there was one question before that, which is marked as answered. Let me read it to you because I don't feel like it is answered. What are the biggest challenges that quantum sensing is facing currently? So you have mentioned several times that it's in the coming future, it's in the coming future. So why? What are the difficulties?
Yeah, thank you for that question. Of course, there are many quantum sensing applications, and some of them are more at the proof of principle stage, and some of them are more advanced. But if I had to give just one answer, then I would say that it is the transition from laboratory results into usable technologies. And so that's something where the quantum flagship has been very helpful. So for example, in this project Maximal, then we took technologies like the miniaturized sensors and others, and we developed them toward technological application, and that continues in OPM-MEG toward sensors that can be mass produced and that can be used by non-experts. You want eventually that a medical doctor is able to use these devices, and so that requires a higher level of engineering, and it requires robustness. And I think for many of these quantum technologies, that is the point where they are now. They're trying to develop that robustness and manufacturability.
Mm-hmm. So this is very interesting. So what you're saying, if I'm getting it right, is that actually there is no problem such as scaling or rescaling, let's say miniaturizing it, as much as there is a problem with scaling in computing, which has not been yet solved and imagined, in a sense that, so for the sensing field, we already have quite a lot of enough know-hows. We just need this transition, right, to be pushed further.
Yeah, I would say again that this is a heterogeneous field. And so if you look, for example, here at this Miracles project, then part of what they're doing here is to make integrated photonics, which is to say to miniaturize their experiments. And so this is it is at present, it's possible to do a tabletop experiment that builds an interferometer in the mid-infrared. But this project is working to miniaturize that in the same way that the atomic vapor sensors were miniaturized using microfabrication technologies. So this technology is maybe where the atomic vapor sensors were 5 years ago, and they want to develop that miniaturization technology.
All right.
So each of these technologies has to pass through a proof of principle stage, and then a scaling stage, and then integration with existing technologies.
Okay, great. Thanks a lot. So let's go to the next question from Matteo Mascagni, and he's saying just a clarification, so that the 𝗔𝗴𝗲 project does not plan to use quantum sensors. It uses advanced classical sensors.
Yes, thank you for that clarification. I was not, I did not mean to say that these were quantum sensors. I meant to say that this is classical sensing, which gives very valuable information, and it could be made more precise and thus give higher resolution if quantum sensors were used. So in 10 or 20 years, there will be technologies to replace 𝗲𝗲𝗱's classical sensors with quantum sensors. And that this is why I say this is over the horizon. 𝗲𝗲𝗱 is a technology which already exists.
Okay, that's a good detail, because I have also missed this part. And thanks a lot for clarification, Morgan, and for the question, Matteo. We have one more question from Victor Roman, and it is: which maximum resolution could be achieved in brain imaging in a reasonable time frame?
So this is something of a complex question. Part of this is sensor technology, and part of this is brain science. The resolution is better at the outer parts of the brain than it is for the inner parts of the brain, and this is simply because the same amount of current close to the surface generates a stronger signal to be detected than a current at the center. But at the surface, then it is expected that the resolution can be comparable to the distance between the sensors and the source. So given that there is the skull in between, you can expect centimeter scale resolution due to this magnetic sensing technique. I should say that is usually used in conjunction with magnetic resonance imaging, which has millimeter scale resolution, and that's what you see in this picture here. So you see the magnetoencephalography results in pink overlaid on a grayscale structural image, which comes from a traditional magnetic resonance imaging of the brain.
All right. Thanks a lot, Morgan. And let's pass to the next question from 𝗔𝗴𝗲𝗱. And he says that he remembers from earlier OPMM examples that there was a need for external magnetic shielding, which limited their usability quite a lot. Is this still the case, asks 𝗔𝗴𝗲? And if so, how much such small problems are actually limiting the widespread deployment of quantum sensors?
Very good question. So in fact, in just the last few years, there have been the first demonstrations of magnetoencephalography in an outdoor environment, which is to say completely without any magnetic shielding. And also recently at a conference last week, there was announced the acquisition of magnetoencephalography signals in an office, so with the computers running and other sources of magnetic interference. So I'm happy to say that the magnetic shielding is not absolutely required at this point. It is possible to do unshielded magnetoencephalography. That said, those are research results, and so there are no commercial systems that are available that do shielding-free MEG. And also somehow shielding is still a good thing. If you have shielding available, then you would like to have it. If so, how much small problems are actually limiting the widespread and deployment of quantum sensors? Yeah, I would say in general, I think the question is about quantum sensors in general, then there are always small problems. So it could be, for example, the use of liquid helium in the superconducting sensors. That seems like a small problem compared to having the sensitivity and the size, but the use of liquid helium can be a serious impediment for institutions that are not don't want the expense or the challenges of using liquid helium.
Very nice. So I'm also really happy to hear that now the magnetic shielding is not required. And you said it's better to use it still. So would it mean that if we are to put it in the hospital, they should have it, or you think it will work without?
I think if you wanted to install today a magnetoencephalography system in a hospital, then you would want magnetic shielding. But there is a rapid advance in unshielded or weakly shielded mag, which gives you hope that someday, maybe 10 years from now, that shielding will not be necessary for this technique.
All right, great. So we are passing to the next question from Javier Hernandez Zahara. And he is asking what sensors are already available for industrial purposes? And in other words, do you see global industries already pushing for the availability of quantum sensors, or perhaps are they just waiting for general availability? We are missing Thomas here.
Yes, this would be a perfect question for Thomas. So again, sensors, there are many different kinds of sensors, and there are many different industries. And so there are industries that are entirely based on quantum sensing. Well, not entire industries, but there are things which are done in industry which are based on quantum sensing, and the number of activities that are based on quantum sensing is growing as they become available. I think from an industrial perspective, you would like a technology which is available, which is robust, and which solves your problems. And you don't really care whether it's built on quantum technology or whether it's built on classical technology. And so the job of the people building quantum sensors is to get them sufficiently high performance and sufficiently robust and sufficiently available that industry can take them up.
Mm-hmm. Yeah, thanks a lot, Morgan. I have emailed the question to Thomas, and in case he will answer, meantime we are still here, I will of course let know, but otherwise I will email Javier. And what I could add to this, as sensors is very passionate for me, the discipline, and I've been looking at Bosch a lot because they have launched their startup in quantum sensing a little bit. They were searching for launching it when there was the first Quantum World in Munich, so it was not this summer, last summer. And since then they launched because they were trying to see what applications they should actually push forward, and they have and which technology they should pick up. And I think they figured that out. So we are missing a little bit Thomas to say what was this exactly. But I think they have went for the solid state sensors. So for the, I'm not sure which one exactly. And so if Bosch has taken it on board, and there is not yet a product, it will be there soon, I'm sure. And I also know that in the Paris Observatoire, they have produced a great deal of gyroscopes and sensors, gyroscopes and accelerometers. It says it's called accelerometers, which are ready to use. So I'm not sure what is the startup or a company that would sell them, or observatory directly. They are sending them to the satellite, so I'm sure they are ready to sell it to commercially. So from my point of view, there are already quite some products. So regarding big companies, Bosch, I think, is big enough, and it's not the only company in the world. So the prospects are good, I have a feeling. And to this end, there are no more questions. I see people are starting to leave, of course, because this is already past 1, and usually we try to make it in 1 hour. And I think it's a good moment to thank again our speaker, Morgan Mitchell, for taking courageously the job of Thomas Strohm and presenting us an overview about sensing as well, and taking all the questions, even those addressed to Thomas. It was an awesome session, and probably we'll see each other again, because Morgan has a lot to say about magnetometry too. And we will keep you updated about the changes in the course run. So thank you very much, and looking forward to see you in 1 month on the next session.